So here's a rational function that we are going to graph with the same ideas, right? So domain, now because it is a rational function, we have a bottom. The denominator better not be 0, right? So x cubed plus 1 is going to be 0, basically at x equals -1. So we have to throw that out. So this is going to be actually a vertical asymptote, right? So I can write that down here. Vertical asymptote, x equals -1. My domain is everything but -1. In addition to the vertical asymptote, though, because it's a rational function, I probably know I have some horizontal asymptotes too. So I can take the limit as x goes to infinity of my function, and you can see if I divide top and bottom by the highest power, we have the limit as x goes to infinity over 1 over 1 plus 1 over x cubed. This one, of course, goes to 0. And my horizontal asymptote is going to be y equals 1. Okay. Now, what about intercepts? Obviously, if I put in x equals 0, I'm going to get y equals 0. So I'm just going to put that in, and I'm going to leave that. I don't think that I don't have any other ones. Okay, so that was that part. So if I had enough space, I would actually start graphing this right now, and I would just put the asymptotes on and the point and stuff. But because I don't have enough space, I'll leave it all till the end. Now, intervals of increase and decrease. Let's see, I'm going to take the first derivative. Of course, I need to use the quotient rule here. So I've got the bottom times the derivative of the top minus the top times the derivative of the bottom. So these cancel out, right? So this would be 3x to the 5 plus 3x squared minus 3x to the 5. So I eventually have 3x squared over x cubed plus 1 squared. Okay? So my critical points are going to be where the top is equal to 0 and where the bottom is equal to 0. So my critical points, then obviously the top is equal to 0, and the bottom is equal to 0 and -1, right? That's my asymptote. So I can make my sign chart up here, or a sign chart for this derivative. I've got -1 and 0. And we can just, we are looking at this, we're doing a sign chart for this, right? So you can see this thing is always positive, right? Because x squared, and this is where everything is positive. So positive, 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 right? But remembering that there is a asymptote here, okay? So that is that. Now, so my intervals of increase and decrease, it's basically always increasing on these intervals. So I've got negative infinity to -1, -1, 0, 0, infinity. Now, in terms of what's going on at the asymptote, I can take the limit and figure it out. We'll worry about that when we get there. Or I can actually do a sign chart or whatever. There's various possibilities, but we'll worry about that when we get there. Now, as far as max and mins, looks like there's none. Right? Because the doesn't change sign is 0. That's going to be a point of inflection, I think. Okay. So let us look then at the second derivative. Oh, this is just here. We'll just keep this one over here for the time being, because the second derivative is going to then I'm going to have to take the second derivative. It's going to be a little messy. So I've got x cubed plus 1 to the 4th, and then I'll have x cubed plus 1 squared times the derivative of the top, which would be 6x minus the top, which is 3x squared, times the derivative of the bottom, which is then going to be 2 times x cubed plus 1 to the first times the derivative of the x cubed plus 1. So chain rule all around. So this is a little messy. And I need to clean it up because I need to solve for where it's 0. So I can't just leave the mess like I could have in other situations, right? So, but you can see one thing, each one of these terms has at least one x cubed plus 1 in it. So that cancels with that. That 2 becomes a 1. This 4 becomes a 3. So I can rewrite this second derivative like 6x x cubed plus 1 minus, what is this? 9 times 2 is 18. So 18 and x to the 4th, right? And then the bottom is x cubed plus 1 cubed. Okay, so x cubed plus 1 cubed, and then this is going to be 6x to the 4 minus 18x to the 4, so negative 12x to the 4 plus 6x. Okay, now I have to find the points for this because I have to do the sign chart for this to figure out the concavity. Well, of course, we know that negative 1 is going to be one of them. Okay, so that's going to be where the bottom is 0. So I got negative 1. And then what else do we have? Let's look at this top part. So what I have is 6x minus 12x to the 4th is 0. So if I pull out a 6x, then this is 1 minus 2x cubed equals 0. Okay, so one possibility is x equals 0, which makes sense. And then the other possibility will be 1 minus 2x cubed equals 0. So that would be x cubed equals 1/2. So x equals 1 over the cube root of 2. Okay, so negative 1, 0, and 1 over the cube root of 2. Lovely, right? Okay. So now what I have to do, just to make it easier, I'm gonna write this like that. I have to do this sign chart for this function, for this second derivative. All right. So if I put something in that's less than negative 1, so I put in negative 2, this is going to be negative, this is going to be negative, so that's positive, and this is going to be negative, so that's going to be negative. Okay, so we have, all right, did I do that right? Concave. That doesn't seem, something's wrong. Negative, maybe did I have a negative wrong? That would be not fun for me. Figure this out now. That's what I got, right? 6x. Okay, so negative 2. Negative, negative positive here. Yes, okay. Right. So if something doesn't quite make sense, go back over the math, right? So you might have made a mistake, and that's what I did, because this term will be positive if I put in a negative 2, obviously. Okay. So let's see, if I put in a negative 1/2, but something between negative 1 and 0, so this would be positive, this would be negative, and if I put in negative 1/2 here, this would be positive, 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 negative. So this part is negative. right? Now, let me think. I actually worked this out. So, this 1 over the cube root of 2, it's something like 0.79. Okay, so it's like 0.8. All right, so if I put in 1/2 is in here, right? So if I put in 1/2, I've got positive, positive, positive. That makes sense, all right? That makes sense because then it makes 0, this is the asymptote, but that makes 0 a point of inflection, which is sort of what we had suspected from here, because that is going to be like that, right? And then let me put in something, okay, bigger than 1 over cube root of 2. So if I put in 1, I've got positive, positive, negative, I've got something negative. Okay, so we have 2 points of inflection. So my concavity, I'm concave up from -infinity to my asymptote and from 0 to 1. And I'm concave down from -1 to 0 and from, oh no, this is not 1. This is 1 over the cube root of 2, okay? And from this 1 over cube root of 2 to infinity. And so my points of inflection, 1 are going to be 0 and 1 over the cube root of 2. So 0, 0, right? And then what's the value at 1 over cube root of 2? F of 1 over cube root of 2. Of course, this is going to be 1/2 over 1/2 plus 1. So 1/2 over 3/2. So it's going to be 1/3. Okay. So 1 over the cube root of 2 and 1/3. Okay. So now I have to put all this together and graph the graph. And we don't have as many points on the graph because than, like, say, the previous one, because we don't have a max and a min. That's okay. I'm going to try to make it big, or at least, because, like, the 1 over square root of 2, cube root of 2, 1/3, etc. So this is going to be my 1, 2, 1, 2. Okay. So I know I have my horizontal asymptote, my vertical asymptote is what I just drew at x equals -1. And I have a horizontal asymptote at y equals 1. Now do remember, we can't cross a vertical asymptote, but we could conceivably cross a horizontal asymptote. I think we are going to be crossing a horizontal asymptote, maybe not. Okay. So what else do I have? I've got the point at 0, 0, right? And I've also got this point at basically 0.8 and 1/3, so that's like here. Okay. Now, so I know that I have to be, I'm going to start from the left, right? I know I've got this horizontal asymptote, I've got this vertical asymptote, and I've got a function in this period of time here, which is always increasing and concave up. And if I look at this function, right, if I look at this, if I'm on the left-hand side of -1, right, then this is going to be something something negative on top, and then like if I put in -2, right, it would be something negative on the bottom. So this is going to be, the function itself is going to be positive, right? So it makes sense. It's going to do this. Okay? Now, if I'm on the right-hand side of -1, though, and I take the limit going this way, I'm actually going to get a negative value because this is negative, and this one, because it's not big enough, right, it's not going to be positive. So negative, positive, so it's, my function down here is going to be negative. And it makes sense. What's going to happen is precisely this, right? My function is now increasing from negative infinity. It's going to get nice and flat here, right? So I have concave down, and then it's going to do a little doohickey here because from 0 to this 1 cube root of 2, it's actually concave up. So it's going to go, it flattened out, and then it's going to do this, but then it's going to turn around and do this, okay? Because I have to be going to y equals 1 at the end. This is, both of these are points of inflection. You can see it's concave down, concave up, and then concave down again. Okay? So without the calculus, without taking the second derivative and finding this other point, you wouldn't be able to sort of see that it did that there. You would just maybe think it goes like that.